All right. I want to wrap it up within an hour, so and I don't want to tax you guys too much, so I'll just go for an hour. And if you feel tired or are unable to concentrate, let me know. Okay. All right. So we were talking about the prescription for how to solve a quantum mechanics problem. All right. You first start with this time dependent equation, which is I cross dou by dou t psi equals h psi. Okay, you guys probably by now know what h is. Okay, the Hamiltonian operator is okay minus h bar square over 2m dou square by dou x square plus v. Okay, that is your Hamiltonian operator. Okay, and then you do separation of variables by doing this psi of x comma t equals psi of x phi of t, and then you get two equations, one for e, this ih cross dou by dou t psi equals e psi, and h psi equals e psi. Sorry, this must be phi. Okay, h psi equals e psi. So there are two different equations, and this is the time independent equation, whatever. Okay, and then you solve this equation, you get those solutions. The solutions are going to be psi n, depending upon the problem, the signs could be completely different, which also satisfy the orthogonality condition psi m psi n dx is delta mn. Okay, that's orthogonality condition. And another condition that it satisfies is integral psi m square dx equals 1. Okay, these psi n's, these solutions satisfy these two conditions, orthogonality and normalization conditions. And the next step is to write your general solution as a summation over n psi n phi of t, phi n of t. Okay, with a constant Cn. Okay, so these are the prescriptions. This is basically the procedure that you take to solve any quantum mechanics problem. Simple problems can be easily solved just by using this procedure, this particular procedure. Okay, so this is exactly what we did with the infinite potential well. Okay, we split it up and we got the time independent equation, and we solved this, and we found the signs. They're just sine kx with specific k's, which is n pi over a, and then we found out what the E is in terms of k. Okay, and then we collected all of them together and wrote a general solution. All right.
Yes, sir.
So far so good. Okay. Okay.
Yes.
Now the point that I wanted to make was, what are these CNs? Okay, as I told you guys before, if you go to this this Hilbert space, I talked about Hilbert space. Okay, where each vector is a function. Okay, this is just an abstract way of denoting a function. A function as a vector is an abstract way. It has not, there is nothing, don't think too much about it. Okay, these are just vectors that are orthogonal to each other, just like your vectors in a three-dimensional space ijk. Okay, these are vectors, many vectors, infinite number of vectors, which are all orthogonal to each other. So this is psi 1, psi 2, psi 3, psi 4, and all that, and each one of them are orthogonal to each other in the sense that psi m, psi n, psi m star, psi m dx is delta mn. Okay, if they are the same, it is 1. If they are different, it is 0. Okay, so so every any general function can be written as a linear combination of all this. Okay, which is the step 5 here, this point. Okay, and where did that go? Okay, and if you take any vector r, this can be a linear combination of the psi 1, psi 2, psi 3, and psi 4, and the coefficients of the linear combination are CNs, right? So you're going to multiply C1 psi 1 plus C2 psi 2 plus C3 psi 3 and all that. You go on like that. Okay, this is your full general solution. All right. Of course, you have the time dependence attached to these psi ones. The psi ones are not just x; they are also x comma t. Okay, these are all x comma t. Okay, now this goal is, what are these C1s? What are these C2, C3, C4, and all that? How do you find these coefficients? Okay, let's say you prepare your system in some linear combination of this, the psi1, psi2, psi3, and all that. Okay, the C1, C2, C3s are determined by your initial conditions. Okay, so these are determined by initial condition. Basically, what that means is psi of x comma 0. X comma, this 0 is, this is t equals 0. At t equals 0, what is your wave function? Okay, that determines the C1, C2, C3, and all that. And once you fix your psi at t equals 0, at all other times, at all the times after that, you have your particle's wave function is completely specified. Once you specify this, okay, and if you know, once you know this these eigenfunctions, this psi1, psi2, psi3, you can figure out C1, C2, C3, and once you're done with that, you can predict your the particle's wave function for all times to come. Okay, it's just like Newtonian mechanics, where if you have a particle that is rolling down, and once you at time t equals 0, once you know the position of that particle, then you can predict the path of the particle at any point, at any time later, right? Right? And just like that, yeah. And at a time t equals 0, if you know the function, wave function at time t equals 0, you can predict the wave function at any other time. Okay. So basically, this is the entire prescription of quantum mechanics. And how do you calculate this? Yeah.
So like, is there any the general form of C1, C2, C3?
Yes, exactly. That is what I'm going to right now. That is what I want to do right now. Yes.
Okay.
So yeah, I'm going to tell you how. Okay, psi1 plus C2 psi2 plus C3 psi3 and all that. Okay, these are just complex numbers. This is just a complex number. Okay, all these are just complex numbers, by the way. C1, C2, C3, and all of them are just complex numbers. These are constants. But how do you find those constants? Okay, once you know, I told you guys, you need to know x of 0, x comma 0, psi of x comma 0. That's time t equals 0. Once you know that, you can find C1, C2, C3. How? This is how. Psi of x comma 0, integrate over psi 1. So let's take star. If it is complex, you take complex conjugate, tx. What would it give you? Anybody? So this is that at t comma at x comma 0. So basically, this is C1 psi x comma 0 plus C2 psi x comma 0 plus C3 psi x comma 0 and all that. Okay, so what is this? Anybody? Psi 1, psi 2, psi 3 and all that. Sorry. This psi x comma 0 is C1 psi 1 x comma 0 plus C2 psi 2 x comma 0 plus C3 psi 3 x comma 0 and so on. Okay, so you can substitute this here, right?
Yes.
Okay, and when you do that, when you integrate it, what is going to happen? This psi 1, there is a psi 1 here. This and this multiplied will give you some number. This and this multiplied will give you
1.
no psi 1 psi 2. Integral psi 2 psi 1 dx will give you what? These are orthogonal functions. It's like I dot j.
0.
Yeah, this is 0. For any other psi 1, psi 2, psi 3, psi 4, this is 0. Okay, so what survives is just C1.
Only C1.
Yes, what survives is just C1. Everything else goes to 0 because those functions are orthogonal. It is like you have some R vector, you have some AI plus BJ plus CK. How do you find out A? You just do R dot I. What is R dot I? It's A, right? That is exactly what I'm doing here. So psi is like R, the psi 1 is like I, okay, and C1 is like A. Does it make sense?
Yes, sir.
Okay, because this psi 1, psi 2, psi 3 are all orthogonal to each other, just like IJKs. Okay, this is how you extract C1, C2, C3. Given the initial condition, you can easily extract C1, C2, C3 just by integrating with all the different basis functions. So integral psi of x comma 0 star psi 1 of x comma 0 dx is C1. Psi of x comma 0, this is your initial condition, by the way. This is not psi 1, psi 2, psi 3. Okay, psi 2 x comma 0 dx is C2, and so on. Right? So when you multiply this by, this is like I, this is like R, this is like A in the previous slide. Okay.
Sir, one question.
Yeah.
Will the value of C1 be given, or we have to find out from the question?
Okay. It is, you have to do this integration to find the value of C1. Once you're given this, okay, and you know this, you can find the value of C1. Okay, if you're given this, if you're given the initial conditions, any problem, if you get any problem with differential equations, you will have initial conditions and boundary conditions, right? Those are two different things, right? You guys know that. Initial condition is when t equals 0. Boundary conditions depends on space. Like it's like v of x equals 0, x less than 0 is infinity. This is a boundary condition. V of x greater than a is infinity. This is a boundary condition. Okay. Similarly, psi of x comma 0, psi of x comma 0 is, let's say, e power minus x square. This is the initial condition. Okay, this is at t equals 0. That's initial condition. Okay, so both of these are given to you. This is given and this is given. In any quantum mechanics problems, you will see both of these, initial and boundary conditions. Okay.
Okay, then after integrating with it with psi 1, the result will be called as C1.
Whatever you get is C1, basically. That is the coefficient that goes with psi 1 in the expansion of psi. So psi of x comma t is some C1
So,
psi
sir, we'll
1.
just write the term after replacing that psi star x comma 0 with root 2 by sine n pi x by a.
Can you say that again? Can you say that again? Hello?
So we can like find Cn term then by replacing that psi star x comma 0 with the root 2 by sine n pi x by a.
Yeah. That, no, psi 1 and psi 2 are those. Psi 1, psi 2, those are the psi 1 equals square root of 2 over a sine pi
N pi x.
ax. Okay, psi 2 is square root of 2 over a sine 2 pi over a x. Right? These are the functions. But psi of x comma 0, this is the initial condition. This doesn't have to be a sine function. This can be any other function. This can be any function. This can be a function like this.
Okay.
This can be just like a function like that, or a triangular function. It can be any function. Okay. Okay, we don't know what this function is. If you're given a problem to solve, then you will get this function. You will get the functional form. Okay, in the question. Okay, you're not going to see these type of questions in your exams. Don't worry. Okay, not already, not in your first year. Okay, this is going to take some time, but I'm preparing you guys for getting into quantum mechanics. Okay, I'm trying to teach you guys the machinery of quantum mechanics. When people say they do quantum mechanics, this is what they do. This is what they calculate. These are the things that they calculate. Okay, they calculate the eigenfunctions, they calculate the eigenvalues, and then they write down the general equation by summing over a lot of eigenfunctions with some constants, and then they apply the boundary condition and find out those constants. That's what they do. That's it. Does it make sense?
Yes.
Okay. Okay. If you're in any doubt, you can always go back to Griffith's second chapter and read through that. It's an extremely well written book. It's a very well written book. Okay, and I've made some comments there as well. If you open the PDF, you can see that there are some places where I've commented also. Okay, what to read and what not to read. Okay. All right. So basically, that is it with infinite potential well. Okay. So infinite potential well, you have the eigenfunctions. The eigenvalue En is n square pi square h bar square over 2m a square. Okay. This is your these are your eigenvalues. Okay. These are your eigenfunctions. Okay. And any function can be written in terms of the eigenfunctions. Any general solution can be written in terms of a linear combination of the eigenfunctions. Okay. Okay. All right. Let's go to the next problem. There are only two problems that I'm solving for quantum mechanics. One is the particle in a box, which is extremely prevalent. I mean, it's basically that is the first step any quantum mechanics person would take to solve particle in a box. Okay, it's a classic problem. Okay, so now you guys know what a particle in a box a problem is, how to solve quantum mechanically, how to solve that problem. Okay, are you guys clear about that? Are there any doubts? Okay, it looks mathematical. But there is a lot of intuition behind it as well. Any doubt so far? You guys are okay?
Yes, sir.
Okay, so let's go to the second problem, free particle. What do you mean by free particle? What do I mean by free particle? When I say free particle, I mean V equals 0. There is no potential everywhere. V equals 0 everywhere for all space. V equals 0 for all space. All right. So now what is the solution for Schrödinger's equation? Okay. Let's say we split the time, we split the Schrödinger equation into time independent part and time dependent part. Okay, and up to that point there is no potential involved. Okay, so up to that point it's IH cross dou by dou t psi phi equals E phi and minus h bar square over 2m this dou square plus V psi equals E psi. Okay, so up to this point we haven't talked anything about the potential V. Okay, now for free particle what I'm saying is this V is 0. Okay, so what is my solution? What is my solution? It's minus h bar square over 2m dou square psi by dou x square equals E psi. Okay, we can do the same thing like we did before and write this as dou x square equals minus k square psi, where k square is 2me over h bar square. I'm just rewriting it. Okay, k is your wave vector. It's 2 pi over lambda. K is just 2 pi over lambda. Lambda is your particle waves wavelength. Okay, now what is the solution for this? I wrote down this morning. What is the solution for this equation? When you differentiate something twice, you get a negative of that function. I'm sorry? Can you say that again? We've been solving this kind of equation since 2 days. Dou phi by dou t equals E phi. Okay, what is the solution for this now? Solution for this is e power minus I E t over h cross.
A sin k x plus b cos k x.
Okay, good. So for the other one, minus h bar, sorry, let's write the other way. So dou square psi by dou x square equals minus k square psi. The solution is psi
E
equals
raised to plus minus
a
e
sin kx plus b cos kx, or I wrote down the other one also, c e power I kx plus d e power minus I kx. Right? These two are equivalent. They are equivalent. Okay. Am I right?
Yes.
Okay, they are equivalent. You can prove this equivalency. If you want, you can just sit down at home and figure out how C and A and B and D are related if they are equivalent. They are all related, by the way. Okay, you can always write it this way or that way. It doesn't matter. Okay, now instead of taking this, we'll take this. Okay, you can take either, but it's easier to take this. Okay, now what are the boundary conditions? Are there any boundary conditions? It's a free particle, so are there any boundary conditions?
No.
No boundary conditions. There are no boundary conditions. So basically your solution is just some e power I kx plus d e power minus I kx. Okay. So this is my psi. How do you determine C and D? There are no boundaries. Earlier, we used normalization. Remember, we used normalization to find the square root of 2 over a for the sine function, right?
Integral size mod psi square equal to 1.
T square x equals to 1. Good. Okay. So now let's do this. Let's do this. So let's just take psi equals e power I kx. Let's forget about so c e power I kx. Let's forget about the minus I kx for now. Okay, forget about that. So now the particle is free particle, which means it can go anywhere from minus infinity to infinity, right? Am I right?
Yes.
So modulus of psi square dx is integral minus infinity to infinity. What is modulus of psi for this? C. Okay, C. So modulus of psi square is c square dx equals what? C square into infinity. Okay, so this is infinity. So now, can this function be normalized? Okay, so what does this mean? C square is infinity. So C, C square. Sorry, C is 1 over infinity, which is 0. Okay, so the function becomes 0. So you cannot normalize it. So these solutions, psi equals c e power I kx, these are called plane wave solutions. Okay, these are non-normalizable. This cannot be normalized. They are non-normalizable. Okay, these are not. These are
So
kind
why
of.
plane wave solution?
I'm sorry.
So why it's called plane wave solution?
Okay, so now let's go back to our wave equation. U of x comma t, the wave equation. The solution we wrote down was e power I kx minus omega t. Right? Do you remember?
Yes, sir.
You remember this is the wave equation, right?
Yes.
So at time t equals 0, it is just e power I kx. It's a plane wave. Okay, the wave goes on like this forever on this side and that side. The wave goes to minus infinity and plus infinity all the way, no change. Just oscillates up and down and up and down and up and down. Okay, so that is the reason. It's basically it's a plane wave solution. The solution itself is a plane wave. It describes a wave. Okay.
Okay, sir.
Okay. So this is non-normalizable, and these functions then cannot be used to determine a particle. This does not describe a particle wave. This cannot describe a particle wave because these are non-normalizable. If you don't know how much of the wave function is there in a particular place, how would you know? How would you calculate the probability? If you don't know c, how would you calculate the probability? It's not possible, right? So these are non-normalizable. So what is the solution? How do you solve this issue? Okay, we solved the Schrödinger's equation. We got these solutions, nice solutions, but they are not normalizable. Now, again, superposition principle comes to rescue. Okay, but this time in a completely different, in a different guise, in a different garb. Okay, remember, what are these k's, by the way? The k, what is k?
N pi by a.
No, that was only in the particle in a box. Here we did not say that. There is no quantization. The particle is not confined between 0 and a. There is no a. There is no small a here. The particle is a free particle. It's not confined. We did not derive any condition for k. We just said when we where was that? Okay, we just said this: k square equals 2me over h bar square. For solving solving this equation, okay, we just replaced all these bunches of numbers, these bunch of parameters h, m, and e together into, we clubbed all of them together into one single parameter. That's k. Okay, that's a wave vector, and wave vector k is, oh boy, okay, k square is 2me over h bar square. Okay, and the e can be any number. Here it is not quantized. E is not quantized because there are no boundaries. It's not constrained. The wave function is not constrained. There are no boundaries. In the particle in a box case, there were boundaries, and the wave was constrained to go to 0 at the ends. And that is how you got the discreteness. Here, there is no discreteness. E can take any value whatsoever, any real value. Okay, E can be continuous, and K can be continuous. K can take any value. If E can take any value, K can take any value. Okay, m is the mass of the particle. If it's an electron, it's just me. H is a universal constant, but E is the only variable you have, only parameter you have, and E varies continuously, which means K varies continuously. Okay, so your solution can be like psi equals c for I k1x, for some value k1, some real number k1, or it can be a d for I k2x. For some value k2, it can be 1.5. This can be 2.3, whatever number, some numbers. It's 2 pi over lambda. These numbers are. Or some other value e power I k3x. It can be any number. The k can be any number. This can be 1000.5. This can be any number. K can be any number. Okay. Now bring in the superposition principle, like we did in your simple harmonic oscillator. Now the total wave function can be sum over Cn, all these wave functions, right? K1, K2, K3, and all that. E power I knx, right? Any of these K1s, K1, K2, but K1, K2, K3 are not discrete, they are continuous. So what do I do? Instead of summation, you go to integration. Am I right?
But the limits will be from minus infinity to infinity, though.
Exactly. The limit is from minus infinity to infinity. Yes. Yes. The limit is from minus infinity to infinity, and this C of n becomes a function of k, because the k is the one that varies. Right? Am I right? So the C.
So then, like, to find Cn in the previous case, we made a use of that initial condition by putting d equal to 0. Then we made use of the equation, and then we found Cn. But in this, how will we find them?
Exactly. Yes. Good question. We are going there. We are reaching there. I'm going to show you how. Okay. So the Cn is a function of k, right? For every k, there is a particular C. Am I right? For k1, there is a C. For k2, there is a D. For k3, there is a E. So for every k, there is a constant. So for this C becomes a function of k for in the continuous case. Am I right?
Yes.
Am I right? So it's e power I kx, dk. We are integrating, we are summing over all n's here. Now the n is continuous, which is k. The k is the one that varies continuously. So integration is over dk. Am I right? Am I right or wrong?
C is a function of k, and meaning what happened to n then?
Okay, we removed n. N is the discrete variable, but this is continuous. So we just moved from n, we just moved to discrete. So basically these are discrete Cn's. These Cn's are discrete. But because the n is continuous, this becomes a continuous function, and this is a function. Okay. Basically the n is gone, and it became a continuous function.
Okay, sir, understood.
Do you understand? So it's like this. So you have a function. Let's say this is your Cn. Okay, for n equals 1, you have some Cn. N equals 2, you have some Cn. N equals 3, you have some other Cn, and it goes on like that. Okay. Now the n basically the n is so the distance between these is shrunk quite a bit. Okay, so basically you're compressing this. So what happens? You're compressing the distance between these lines. You're making them continuous. So what happens? You get something like this, right? You get something like this with the lines are so closely spaced. Am I right?
Yes,
As
divided into
then this becomes a function, right? And that is your ck. Does it make sense? Okay.
Yes.
Now you look at this function. Look at this psi of x equals integral c of k e power I kx dk minus infinity to plus infinity. Does it strike like anything to you? Does this equation ring a bell? What is this equation? Anybody?
Gamma function.
No. Anybody? This is just Fourier transform. This is just Fourier transform. This is simple Fourier transform. This is what you do with Fourier transform. Yeah, g of k equals some f of x e power I kx dx. And f of x equals integral g of k e power minus I kx dk. This is Fourier transform. Don't you guys know that? You guys know this, right? Yes or no?
So you had introduced it, yes.
I'm sorry?
You had told about this.
Yeah. I told you guys to go through Fourier transforms. I think I remember I taught you guys a little bit of Fourier transforms. I did not go entirely deep, but I wanted you guys to learn Fourier transforms. This is why.
Yes.
Okay. So this is basically Fourier transforms. It's nothing but a Fourier transform. Okay. So you can write your total wave function as a combination, a linear combination of a lot of these basis functions. These are the basis functions. These are your eigenfunctions. And these are your coefficients. Okay. And you're going to, this is, you're summing over all the eigenfunctions. Here, because the eigenfunctions are continuous, you're integrating over all the eigenfunctions. Okay. And you're getting your wave function. This is your wave function. Now the question, is your wave function normalizable? Is this psi of x normalizable or non-normalizable? E power ikx is not normalizable. We saw that. It goes to infinity. When you integrate, when you try to integrate it, it goes to infinity. But what about psi of x? What you did was to take a lot of these infinite extent functions that are non-normalizable, you combine them together as a superposition with some superposition constant, c of k, and then you integrate over that, and you got a new function, psi of x. Is this function normalizable?
But for that, we need to know what is C of K, right? Like,
Good, very good. Very good. We need to know
integration
what is C of k.
Yes.
Yes.
Size are equal to integration from minus infinity to infinity C K ka square dx.
Very good. We need to know C of k, right? Okay. Now, what do you think is the relationship between C of k and psi of x? Okay, C of k, you have, this is some function C of k. Okay, this is k. You have some function C of k. And then you have another function psi of x. Okay, this is x. You have some function. What do you think is the relationship between these two? The relationship is basically Fourier transform, right? You take a Fourier transform of this, you get this. You take a Fourier transform of this, you get this. Am I right?
Yes, based on the last equation you're doing.
Yeah, psi of x is integral C of k e power I kx dk. And C of k is integral psi of x e power minus I kx dx. That's it. Because this is a Fourier transform. Okay, you know psi of k if you know psi of x. You know psi of x if you know C of k. Okay, and this, here comes the beauty. Okay, let's say your C of k, let's say your C of k is a delta function, like it is like it is one at a very specific point at some k equals k naught. Okay, this is k, this is C of k. Okay, it's one at a very specific point at some k equals k naught, it's one. Everywhere else it is zero. So what happens to that integral? Oops, I think my, yeah, it just crashed. Hold on. My OneNote just crashed. Okay, so this is delta function, meaning that this is delta k minus k naught. Okay, it's called a delta function. So now what happens to my psi of x? Psi of x is c of k e power I kx dk, right? Right. My c of k is now delta k minus k naught, which means this is 0 if k is not equal to k naught. If k not equal to k naught, it's 0. It's 1 if, sorry, infinity if k equals k naught. Okay, it goes up to infinity. The integral is 1. Okay. So now if this is the function, then what happens is this integral becomes e power I k naught x. Psi of x is e power I k naught x. Okay, basically if you have a delta function, you just replace this with whatever is here. Replace this ikx with the k naught. The k becomes k naught. That's it. Because when k is not equal to k naught, this is 0. So only at k equals k naught, the function has any value at all. So your psi x becomes e power I k naught x.
So could you explain this part again?
So basically, this is a property of a delta function, right? You guys not have not come across delta function yet. I introduced Kronecker delta, like this is m equals for m equals n. This is 1. For m not equal to n, this is 0. We talked about this, right? This morning. This is Kronecker delta.
Yes, yes.
Similarly, we have delta function k minus k naught. Delta k minus k naught. This is continuous form. This is a discrete version of a delta function. This is continuous version of the delta function. Okay, this is continuous version of the delta function. K minus delta of k minus k naught. So this is 1 if k equals k naught. Why do I do that? K equals k naught, and is infinity if k naught 0 if k not equal to this k naught, and infinity if k equals k naught. Okay, and integral of delta k minus k naught dk equals 1. Okay, that's the definition of this delta function. So what it does is basically if you're integrating with some f of k delta k minus k naught dk, then what it does is basically replace this k with a k naught. That's it. So this k naught goes here, f of k naught. That's it. Basically, it picks out the function's value at k naught. That's all it does. The delta function picks out only the value of the function at k naught, and it makes everywhere else 0. Understood?
Yes, sir.
Okay. Now let's go back to that equation. Psi of x equals integral c of k e power I kx dk. This is my Fourier transform, and this is also my general solution for the free particle. The psi of x is the general solution for the free particle at t equals 0. Let's just take t equals 0 to make life simple. Okay, this is the general solution, right? Now what I'm saying is, let's say my ck is delta k minus k naught. That's what I'm saying. I'm saying in the function c of k has a strong peak at k naught, and everywhere else it is 0. If this is the case, what happens to psi naught? What happens to psi naught is this k naught x. Psi naught becomes psi of x becomes e power I k naught x. Okay, now you plot psi of x. How do you plot psi of x? It's e power I k x. Let's just plot its modulus. It's 1. Let's just plot modulus of x for all x. It is just 1, right?
Yes.
Okay. You see this relationship. C of k is sharply peaked whereas psi of x is broadly distributed.
So, but then we just assume C of k to be that delta k minus k naught. Like we did not really find out what was its real equation.
No,
Why
you
did
don't
we
know what the
assume
relation is, but I'm trying to give you guys some limits. So in the limit where C of k is very sharply distributed, C of k is very sharply distributed. In the limit C of k is sharply distributed, psi of x is very broadly distributed. That's what I'm saying. I'm trying to teach you guys something. Okay? Let's go to the other side. Let's say C of k is broadly distributed. This is k. What do you think will psi of x look like?
a sharp peak?
Wonderful. Exactly. A sharp peak. If C of k is broadly distributed, psi of x is sharply distributed. Okay. How do you say what a function, how a function is sharp or broad? How do you say that? If you have a function, some function, how do you say this is sharp or broad?
The range of x, like if it is at only one particular point, it will go to infinity. Others in a particular range of x, it will have some height.
Can you put a number? Can you do a metric, a measurement?
Amplitude ratio.
What about variance? What about variance? Have you guys heard of variance? Do you guys know what a variance is? Do you guys know what a standard deviation is?
In probability, I think.
Yeah, this also applies to functions. If the function is broad, its standard deviation is high. If a function is narrow, its standard deviation is small. Its variance is small. If a function is broad, its variance is high. Right? Right? So you can measure the variance of these things. Am I right? So the variance of this curve is very high. It's infinity actually. The variance of this one is actually 0. Right? So in general, if you have C of k is like this with a broad variance, high variance, then psi of x has small variance, and vice versa. So this is C of k. You have broad wave function, it's a broad C function. Okay, this is k, and this is psi of x, and this is sharp. Okay, this is x. So basically, this distance is delta k, and this distance is delta x. Right? This is the uncertainty in k, right?
Yes.
This is the uncertainty in k. This is uncertainty in x. Am I right? If the uncertainty in k is large, the uncertainty in x is small. If the uncertainty in x is k is small, uncertainty in x is large. What is this? What is this? What relationship is that? Come on, guys. You guys know. Delta k.
Heisenberg.
Uncertainty principle. Exactly. Heisenberg's uncertainty principle. That is exactly what it is. Delta k times delta x is some greater than or equal to some constant. Okay. When delta k is large, delta x is small. When delta x is large, delta k is small. This is uncertainty principle. This comes right out of Fourier transforms. Are you guys confused?
So like delta k into delta x will be a constant when.
Uncertainty principle.
I'm sorry?
Is it similar to Heisenberg's uncertainty principle?
It is not similar. It is Heisenberg uncertainty principle. For Heisenberg uncertainty principle, delta p, delta x, p is just h cross k. Right? You guys know this. P is h cross k.
Yes.
So this is uncertainty principle.
So that means when you say delta k into delta x equal to constant, like graphically, what does it represent?
Okay, I'm going to give you intuition, the intuitive picture, why this is the case. Okay, let's go back to our original equation. Psi of x is C of k e power I kx dk. So what am I doing here? What am I doing here? What am I doing? So I'm going to make it simple. Let's say, so I'm taking a wave, a plane wave. This is e power I kx. Let's say k1x. And I'm multiplying it with some c1. And I'm adding it with another wave. This is e power I k2x. And I'm multiplying it by some c2. And I am taking another wave. This is e power I k3x. Okay, the lambdas are different. You see this? The lambdas are different. This is a different lambda. This is a different lambda. This is a different lambda. And that is why you have k3s are different. K1, K2, K3 are different. K is just 2 pi over lambda, by the way. Okay, and I'm multiplying this by C3 and so on. I'm doing this all over. And then I'm summing them all up, plus, plus, plus. So what do you think I will get?
A single wave.
Another wave? Now, the question is this wave, does this wave go from minus infinity to infinity, or is it going to be localized? Something like this. That depends on what you choose as C1, C2, C3, right?
Depend on what C of k, what kind of function it is.
Yes. So if I just choose C2 and make everything else 0, okay, if I just choose k, just let's say just k2, only for k2 the C2 is not 0, everything else is 0. So is this function localized or not delocalized? What is my psi of x?
You will get the C2 ka graph, the wave
It
of
is just
C2.
e power I k2x. It is just e power I k2x. I'm just going to get that because everything else is 0. C1 is 0, C3 is 0, all others are 0. So my psi of x is just e power I k2x. Am I right?
Yes.
So your wave function goes from minus infinity to infinity. It is not non-zero. It's not 0 anywhere else. It is spread out. Whereas in the k, I am purely localized. Only for k2, my C2 is non-zero. So only at k2, in the k space, only at k2 I have a peak. Everywhere else I have a 0. It is completely localized in k space and completely delocalized in the momentum space. Right?
Yes.
Right. So if I have to make a small wave here, a wave that is confined, I have to add a lot of c's because these are infinite functions. These functions e power I k1x, k2x, k3x, they're all infinite functions. I have to add a lot of c's to get a wave that is confined between, let's say, minus a and plus a in a small region. If I want to confine in the x space, in the position space, if I want to confine a function, I have to add a lot of different plane waves with different k's. So I have to spread in k space. I have to spread c. The c must be hugely spread so as to make something sharp in the x space. If the c in the k space, this is k space, right? In the k space, if it is sharply peaked, in the x space, it is broadly, it's broad. In the k space, if it is broad, in the x space, it is sharp. Does it make sense? You have to integrate over a lot of k's to get some localized function. If you want a localized function, you have to add a lot of k's together. Remember beats? Remember beats? Do you guys remember beats? Right? You add two waves that are slightly different from each other, and what you get is this kind of behavior, right? This kind of behavior. Right? Okay, you see some kind of a localization here. If you add more and more, some of them will become smaller. Okay, it'll become like this. By the way, sorry. If you add more and more, let's say if you add three waves, if you had three waves like this, one plus slightly different another one plus slightly different another one, if you had three waves, then you will see something like this. Something like that. The wave looks localized. Okay, if you keep adding more and more and more, I'm sorry.
It will be envelope kind of.
Yeah, it is an envelope, exactly. It'll be an envelope. If you add more and more and more waves, then you will see something like this. Something like this. Okay, with a lot of small waves in between, like this.
Yes.
Whatever. Okay, with a lot of mini waves here. It'll be like this. Okay, it'll be like an envelope. You have a group of waves. This is group of waves traveling together. Okay, and you'll see the wave, it's localized, and this is called a wave packet. You guys have read about this, right? Wave packet. Have you guys read about a wave packet? Yes or
yes,
no?
and signal transmission.
Oh no, that's not that's a different one.
Not the message and carrier wave kind of.
Okay, no, maybe that is a different one. Yeah, in computer science, whenever you transmit something, we call that a packet, but that packet is different from this. Okay, here a wave packet means when you add a lot of waves with nearly same frequencies together, what you create is a localized wave packet. This wave packet is localized. It is from -a to a. A is finite. It is not extended like this. This wave goes from -infinity to infinity. I'm sorry.
Also, like beat.
Yeah, these are similar to beats. Okay, these are similar to beats, but in beats you're adding two discrete frequencies. Here you're integrating over a lot of frequencies. These are continuous. The K is continuous here. This is integration. Okay,
Sir,
this is based on integration.
if we keep on adding more waves, then will the range increase or decrease?
Decrease. Decrease. If you add more and more waves, what that means is that you're making the CFK broader and broader, right?
Yes.
Do you understand what I'm saying? If you add more waves, let's say you add more waves with this K here, then you're broadening the CFK, right? Which means you are also shrinking the psi of x along x direction. So this is shrunk, delta x is shrunk, this is large now, delta k. If you add more and more waves, you're going to make it sharper and sharper. The wave packet becomes sharper and sharper. The more k's you add, the more waves with more momenta. The k is momentum. It's h cross k. If there is a lot of momenta involved in your C of k, there is very small spatial distribution of the particle. The particle is localized. If the momentum of the particle is large, if the momentum distribution of the particle, this is the momentum distribution of the particle, the momentum distribution of the particle is large, then the particle is well localized. If the momentum distribution of the particle is sharp, then the particle is delocalized. You understand that? Do you guys understand that?
Yes.
Yes.
Okay, so basically this is uncertainty principle, and uncertainty principle comes directly from Fourier transforms. This is Fourier transform. The relationship between C of k and psi of x is Fourier transform. All right.
Yes, sir.
Okay. So basically, e power ikx, even though these are eigenfunctions of your Hamiltonian, these are eigenfunctions. Dou square over dou x square psi equals e psi. Okay, this is your Hamiltonian. These are your eigenfunctions. Okay, and the energies are continuous energies. Even though these are eigenfunctions, you cannot use these eigenfunctions because these are not normalizable. What you do, you create a linear combination of these eigenfunctions, and that you do by doing this, like C of k e power ikx dk is from -infinity to infinity. Okay, you create a linear combination of this e power ikx, these eigenfunctions, by multiplying them with some constant, and now you're integrating instead of doing summation. Okay, then you get a wave packet that is localized. This is localized wave packet. This is normalizable. This is normalizable. Okay, and this relation encapsulates the whole uncertainty relationship. As I said, delta x delta p is greater than or equal to h cross over 2. It comes from this relationship, this Fourier transform. So Fourier, the uncertainty relationship has everything to do with Fourier transforms and very little to do with quantum mechanics. It is just this h cross that comes from, that is from quantum mechanics. Otherwise, there is no quantum mechanics here. This uncertainty relationship is directly from Fourier transforms. Okay, the more waves you add, the sharper the resultant wave packet is. The less number of waves you add, the broader your wave packet is. That's it. That is the statement of uncertainty principle. Is it clear? Is it clear?
Yes.
Have I been? Did you guys get some intuitive feeling about uncertainty principle?
Yes. Yes.
Okay. Okay. Just one more point, and I'll leave you guys. Just one more thing, and I'll leave you guys. Okay. So your wave packet, let's say your wave of x comma t. Now I'm adding t is e power I kx minus omega t. Okay. Omega is you guys know. Hold on. You guys know E equals h cross omega, right? So omega is E over h cross, right? And E is p square over 2m, which is h cross square k square over 2m. So omega is h cross k square over 2m. Am I right?
Yes, sir.
So far so good. Okay. So now my psi of x comma t is e power I k of x minus h bar k square over 2m t. Okay. Now, what is the velocity of this particle? What is the relationship between omega and c, omega and k? Omega equals
A by V.
ck. Omega is 2 pi nu equals c 2 pi over lambda. Okay. So nu equals c over lambda. C equals nu lambda, right? So omega equals ck, right?
Yes, sir. Yes.
Okay. So you guys, I just showed you guys omega is h cross k square over 2m and k is k. So c is omega over k, right? It's h cross k over 2m. Am I right? Okay. This is the velocity of the particle. It's supposed to be the velocity of the particle, right? But is it really the velocity of the particle? Is this really the velocity of the particle? Hold on, what happened? Okay, something wrong.
What
Anyway,
do you mean really velocity of particles?
Okay, let's. Something is wrong here. Just a minute. Let me. Oh boy. Okay, my system has crashed, I guess. Okay. Okay, my system has crashed. Not this one, my other system where I'm referring my notes. Anyway. Well, just a minute. Let me try to revive my notes. I'm running into trouble. I don't want to miss anything. Just hold on. Okay, I think it is going to take a while. Okay, anyway, so yeah, E is half mv square, right? Am I right? Okay, which is
Yes,
also h cross omega. E is h cross omega, which is also half mv square, right? So h cross omega is h cross square k square over 2m. Am I right? Because omega is h bar k square over 2m. So this is h bar square k square over 2m. Am I right?
yes, sir.
Okay. Now what is v?
Root 2e by m.
2h bar square k square over 2m square. Am I right? So I'm just taking this half m to the other side, to this side. Okay. So this is v square. So v is
V
h plus k over m. Am I right? Yes or no?
yes,
So what I'm getting is this is I'm doing this is classical analysis. This is classical, and this is quantum. Quantum mechanically, what I get is h cross k over 2m. But classically, what I get is h cross k over m. The velocity of the particle here, the c, the velocity of the particle with using quantum mechanics, which is basically from the wave function. So I'm just using the wave function here, this wave function, e power I kx minus omega t, and I'm dividing omega by k. Okay, dividing omega by k, I get h cross over 2m, h cross k over 2m. Whereas if I do it classically, just half mv squared equals h cross omega. Okay, without using the wave function, I get h cross k over m. So is this the velocity of the particle, or is that the velocity of the particle? This is quantum velocity, this is classical velocity. Why are they not agreeing? Any answers? Anybody have any idea why they are not agreeing? Anybody? Any solutions? This has to do with phase velocity versus group velocity. This is what makes the difference. In the previous page, one derivation is phase velocity, one derivation is group velocity. Which one is phase velocity here?
V equal to h bar k by m.
Nope. This is the phase velocity. And this is the group velocity. I'll show you how. I'll show you why. Okay. Phase velocity is the velocity that you get by doing c equals omega over k. Okay, this is your phase. This is phase velocity. This is always phase velocity. Okay, this is how your phase velocity is always defined. How is group velocity defined? Anybody? Anybody? How is group velocity defined? It is defined by dou omega by dou k. Have you guys come across this equation? Yes or no?
No, sir.
No? Okay, this is the equation for group velocity.
So like where can we come across this before?
A derivation of this is in Payne, HJ Payne. Okay, it's in any like if you go to Resnick Halliday, if you go to Griffiths, HJ Payne, any book has this derivation for group velocity. Okay, this is the equation for group velocity. Now omega is h bar k square over 2m, and dou omega by dou k is what? It's just h bar k over m, which is basically the same as b. Okay, so v is group velocity, whereas c equals omega over k is phase velocity, which is basically h bar k over 2m. So phase velocity is only half of group velocity. You guys know what is phase velocity and group velocity, right? Or no? Let me remind you guys. Let me remind you guys. Okay. So I told you guys psi of x equals integral c of k e power I kx dk. Am I right? So basically we have these waves e power I k1x c1 plus some other wave e power I k2x c2 plus and so on, right? I just drew this. This is your Fourier transform, right?
Yes, sir.
K3x and all that. So what is the velocity of these waves, these individual waves? The velocity of these individual waves is the phase velocity. Okay, these are all phase velocity. These individual waves travel with the phase velocity. Okay, and when you group them together, you get another wave, which may be like this, which may look like that. Okay, this is x. Okay, this is psi of x. This is the group of, it's a group of waves. This is basically a group of waves, right? These waves form a group multiplied by this constants, and this is psi of x. This is a group. Okay, and what is the velocity of this wave? This is group velocity, Vg. Okay, the phase velocity is omega over k. Group velocity is dou omega over dou k. The velocity of this group is given by the differential of omega with respect to k. So the wave packet, which corresponds to the particle, moves with group velocity. Okay, it's the particle. Basically, if you want to describe a particle, you have to describe a wave packet. Okay, the wave packet describes a particle. So the particle is between this point and this point. It's somewhere here, somewhere between that and this point. If the particle is massive, this function becomes a delta function. It is precisely localized in a single space because m is very large. Okay, and it's 1 over m. Most of the times, your quantum mechanics gives you 1 over m for spread. Okay, so the spread becomes small and the massive particles becomes well localized. Okay, and its velocity is basically the same as classical velocity. So every particle in quantum mechanics is described by a wave packet. By a wave packet. Okay, and the wave packet, how do you define a wave packet? This is how, using Fourier transforms. So basically, if you consider an electron, a proton, a neutron, quark, whatever, any quantum particle is considered as a wave packet. It's a collection of a lot of plane waves added together, multiplied by some constants and added together. Okay, only the CFKs would differ for different particles. Okay, for an electron that is going around a nucleus, this has a specific CFK. Another electron has another specific CFK. The CFK functional form would differ for different electrons, but the underlying eigenfunctions are the same. Okay, you guys understand this?
Yes, sir.
Yes, sir.
Okay, all right, I'll stop here. It's been a while, so it took quite a while. I'll stop here. Are there any questions?